Okay, let's have a look what technology is about when we compress this kind of data. We found that the point cloud is the convergence between these two worlds, between the world of visual capturing by using cameras, plus sometimes some depth sensors, and the visual synthesis. In the sense that it is a relatively easy to produce representation. It can be of very high quality if the cameras are good quality, but also it gives by design interactivity and immersiveness, in the sense that because it is a 3D graphics representation, we can use a rendering engine to produce whatever viewpoint we need. So we have the immersiveness of the user, but also the user can interact with the content. We are in a pure synthesized world. In few words, what is a point cloud is relatively simple as a representation, is a set of 3D points. They are not ordered like pixels in the image. So there is no relationship between them. Of course, we can compute distances, but there is no index that we can address directly the point. And each point is defined by a 3D coordinate, x, y, z, plus some attributes that are defined per points. We can have colors in different kind of spaces, but we can also have additional attributes like reflectance, transparency, attributes that are used by the 3D graphics engine to when the object is to be rendered. Here are some examples. Probably you already know these examples are coming from sequences that we used for while developing the standard. And this one is obtained. Actually, of course, I present it as a video because we cannot see it in 3D because of our telecommunication system. But what you have to imagine is that when you have a helmet, you can turn around the object and you can see it from different space viewpoints. Some other examples coming from different companies. Here you see a basketball player, and at a certain moment the camera is moving around, and because the object is represented as a 3D object, we can see several viewpoints. And you also notice that the video behind is a 360 video. Another example by Microsoft, when they market the HoloLens, they show this example of a football terrain with people, and everybody here is represented as a 3D object on a field. When we do the mathematics, we realize that for representing one single of this small object, we need something about 1 to 3 gigabits per second per object, which is relatively huge. So it's absolutely clear that we need compression if we want to create meaningful applications. Yeah, some other example. These are applications that are more and more present these days. What you see in this setting, there are two people. One of them is wearing a helmet, an AR helmet. The other one is just dancing. But what this guy can see in the scene, he can see two persons. One is real, and the other one is a person that was captured before and displayed only in the helmet. So it's a kind of AR scenario that is more and more useful today. Not necessarily for dancing, but there are other applications that can be done. And by the way, this person here is represented as a point cloud. Another example, which will have even a bigger impact in our life, is the assisted driving up to autonomous driving. So these systems they are using a LiDAR for creating for capturing the scene, the LiDARs that are on the car, and capturing the scene. And using helping the driver to with some messages, or even going up to having an autonomous car, because he's able to interpret the obstacles, the signs, and so on and so on. This is not something new, but what is new is that we will have in the future systems that are using multiple cars to capture the world, and there will be a transmission of information between cars, and one of this information to be transmitted will be the acquired point cloud. So this is why the compression is also needed in this kind of use cases. Okay, so a simple slide just to have in mind the numbers. An object like this one is using 800,000 points, and if we want to transmit it in an uncompressed version, is about let's say roughly 1 gigabit per second. Okay, at least. So for sure we need compression. Then the question was, what can we do to compress this kind of data? Let's call it signal, because it's captured from the real world. There are some principles here. One is that a point cloud is a very sparse occupancy of the 3D space, because in general the object is represented by the surface. Of course, we are just capturing how the light is reflected by the surface. We have no information about what is inside the volume. And in terms of prediction and in terms of compression, while in 2D a pixel has 8 neighbors, in 3D it has 26, and many of them are transparent. So you may imagine that building the predictors is a more difficult task. As we may imagine, we will not do it directly in the 3D space, but we need some special data structures, special constructs, and the literature already had an intensive research work in this domain. So this is not new, not invented by MPEG. The OC3 and KD3 are two examples of these structures that are used to represent the 3D space into another space, and which are more compression friendly, let's say. Just illustration explaining what the OC3 is. So we have the point cloud here. An OC3, a 3D OC3, will divide the space in cubes, and the idea is to continue this subdivision into cubes only if a big cube is occupied. So when a big cube is not occupied, just signaling is not occupied, there is no need to subdivide it more. But when it is occupied, we continue the subdivision up to the last leaf. And that will change the XYZ representation into a kind of tree where we, as an example here, we encode 1. It means that this cube should be subdivided more. And of course, this is a 2D example. It will be subdivided in 4. And then if there is a need to subdivide, so on and so on. So we may imagine that this hierarchical graph has much more redundancy, that it can be exploited by coding tools than the initial 3D representation. Another one is KD3, but I will not go in detail, is just another way of segmenting the space. So still, there are some issues here, in the sense that these kind of structures are good for static scenes, but we are in MPEG, and one of our objectives is to compress moving pictures, so moving scenes. The problem is that when we do this kind of partitioning for, let's say, one frame of the object, what it may happen is that we have this small cube which is occupied here, and at the next frame, it is possible that this point here jumps somewhere there. but the big cube before was empty. So it means that points from here can jump in the hierarchy very high. And that is not very good for prediction, because we have, let's say, like we have in video, we have to force an intraframe. Okay, so while there are things that can do a good job in for static objects, for dynamic we have to do something else. Okay, so this is what we did. We understood the need of point cloud compression back in 2014, and as all the MPEG projects and in general standardization projects, we start with call for evidence, and then we prepare the data for call for proposal that we had in April 2017. And actually, in April 2017, we had the call for proposal and then the answers in October. And we had 9 leading companies around the world, of course, who answered to that. And we end up in 2020 by FDIS of two standards. One is VPCC and the other one is GPCC. And both are for point cloud. And now the question is why we did 2 standards and not only one. We actually, from the beginning, we observed that the point clouds are different depending on the application. You may have dense point cloud, you may have sparse dense cloud, of course, you may have static or dynamic. So it was quite obvious from the beginning that the same coding tool cannot fit all the requirements. So the first one was the video-based point cloud compression, and the main ideas to create this standard were inspired from graphics. One of this idea is what we call in graphics displacement mapping. So sometimes instead of defining geometry like a set of triangles and attributes, we are generating the geometry based on an elevation map. So by using this image, we can create at the rendering phase a geometry. This is called displacement map, and this is one of the idea we used in VPCC, and I will explain how. The other idea, also inspired from graphics, is the texture mapping, and the way how the objects are colored in 3D graphics is that we have with the geometry an associated texture map where portions of the geometry are projected in this image space, and the color that is in the corresponding pixel will be used to color the 3D point of the object. And everything else between the 2 pixels here in the image or 2 vertices here in the 3D model will be used by copying the value of the corresponding pixel. This is also something well known in 3D graphics. So based on these 2 ideas, the way how we decide to code the point cloud was to have projection planes. So you may imagine this is our object, and then we will project all the points from the object on a plane, and we will encode the distance with respect to the plane, which will give a kind of depth, and the color of that point will be encoded as the color of the pixel in the plane. Okay. Of course, it's not as simple as I'm explaining, in the sense that it may be possible, because we have a 3D object here, to have several points that will be projected in exactly the same plane pixel. And then we have to store different colors and different depths. And to avoid this situation, actually, what we are doing is, instead of projecting the entire object, we are cutting the object in what is called patch, and each patch is projected on one of the planes of a cube. To give even more adaptability, we add 4 additional diagonal planes. So the projection space looks something like this. We have the the cube's faces plus the additional faces, and each patch will be projected to the plane that gives the less projection distortions. Okay. And once it is projected, what we keep is the distance with respect to the plane and the color in the pixel domain. So what this transformation gives, here we have the 3D space that was segmented into patches, projected on different kind of planes, and what we obtain is a geometry image giving the distance of the point with respect to the plane plus the color that is associated to that point. So in one sense, a 3D representation was transformed in a 2D representation by, let's say, an intelligent projection. Of course, not all the pixels, because we are transmitting these images, videos, and we decode them, and we observe that some pixels are not useful for the reconstruction. So we have to signal that to the decoder. So this is why we have an additional occupancy map indicating which of the pixels from these maps are to be reconstructed. That gives a good approximation, but still some points are still projected in exactly the same position in 2D, and this is why we can add as many maps as required. Okay, and that gives a very good approximation. And if at the end of the day we still have points that are not well projected, they will be encoded separately in such a way that we have bijectivity between this 3D space and these collections of 2D maps. Just illustrating that for the walking sequence that you saw before, this 3D object walking is represented now as a set of images, and since MPEG is very good in video coding, we may say the problem is solved. We can use classic video codec to encode this 3D representation. Of course, it's not as straightforward as I'm saying it, because even if you look at these images, you notice that these are not images for which the video codecs were designed. In the video, we have other type of information in the sense that it's more fluid. We can nicely obtain the motion vectors. So this kind of content, let's say, is not video codec friendly, but still is possible to code with video. And the question is now what the group is doing next. In terms of the form of what we call is next is a kind of, we are talking about explorations, about preparation of the proposals and so on. So one of the topics which is in exploration is the AI based compression. This is something that becomes to be very important in general for the technology development, for media compression, because it's not only for 3D graphics, but we have more and more papers and work on showing that AI based methods can provide good compression performances for images, and more now publications related to video coding, and few of them about graphics coding based on AI. So we started an exploration. This is something like 1 year before, 1 year and a half maybe, trying to see what are the possible performances of these approaches for 3D graphics.